And hopefully, can you see that okay?
Yep, brilliant.
You can
Sounds
see
good.
that's all good, is it? Okay, I'll just go to pointer. And then we're away. Can you see my laser pointer flying around as well?
Yep.
Perfect. Yeah, thanks, Mimi. Yeah, absolute pleasure to be able to talk to you today about the work that we've been doing in the area of automation. What I wanted to talk about actually is it sort of hooks into our historical work on understanding Palladium catalyzed cross-coupling reactions, particularly from a mechanistic perspective. But underneath all of that work really is catalyst design and really developing cross-coupling chemistry in a positive way. For the more complex chemistry, and this is where we sort of hook into speciation, catalyst speciation particularly, which is something I mentioned yesterday in Tobias's discussion about his work. It's a really important issue for us, particularly how we might model that in the future. So hopefully I can give some hints about that today as well. So yeah, I've been in New York now 21 years, which seems crazy. And of course, about 20 years, we sort of tried to look back and try and work out what we discovered. I won't go through all of these things really, but just to say we've been on a journey of catalyst design and understanding mechanisms in what would be seemingly homogeneous palladium catalyzed reactions, but we get this sort of hybrid homogeneous heterogeneous behavior. So we looked at general cross couplings like Suzuki couplings, het couplings, Sonneger-Shearers and so on, but also looking at a heterogeneous nature. So we're looking at particles and how surface catalysis can play a role in common Suzuki couplings. We've even developed new catalysts for natural product synthesis and looked at redox cooperativity of NOx anions at palladium as well. So there's some interesting distractions along the way as we've been doing more mechanistic work. Something I'm not going to talk about at all today is our work on manganese, but it is a big part of what we do, particularly collaborating with Jason Lynham. So just to say that we're doing lots more time-resolved, ultra-fast spectroscopic studies with manganese carbonyls and CH functionalization chemistry. So there's been some, I think there's been some big discoveries there in recent years, and we're really looking to develop that going forwards. In terms of palladium and automation, well, we've realized automation is the way forward for us, particularly for improving our mechanistic understanding as well as synthetic methodology development. So that's where I'll go today. Sorry, this is a very complicated slide, but just to show you how I see automation fitting in with everything that we're doing. So we can imagine that we can do high throughput experimental screening in batch. And of course, as we heard from Anna yesterday, you can do that with flow approaches as well. So bringing all of that data together, hopefully we've got lots of useful data on reaction outcomes, which can inform mechanistic details. And of course, you sort of think about your global outcomes here. I won't go through all of these, but many of these were touched on yesterday. But we're particularly interested in the details of catalysis. Mostly about homogeneous processes, but as I say, we've always got this question about the behavior of heterogeneous species as well in our chemistries. That also kind of links to all sorts of other things, and this is kind of, I guess, our traditional work that we would do for mechanistic studies in catalysis and organometallic chemistry. So computation with DFT, which we heard a lot about yesterday. I've mentioned time-resolved infrared spectroscopic analysis, which we do at the Central Laser Facility at RAL. We do lots of work as well at Diamond with XAFs, so X-ray absorption spectroscopy measurements, and that's been particularly useful for nanoparticle catalysis. And of course, we're doing lots of work with NMR and mass spec here in York, particularly in operando, so looking at reaction mixtures directly and getting data out. And that fits together nicely with collaborative work with the groups at Leeds, so Richard Bourne and Charlotte Willens on using their sort of flow setups, flow optimization setups linked to electrocatalysis. Going forward, we're really looking to forge closer links with the computer science department here in York and beyond through Your Robots. So this is a university-wide initiative which is looking at robots in all sorts of forms and just thinking about how we might change the way that we work in chemistry labs in general using robotic systems. So going on to palladium catalysis, I suspect palladium catalyzed cross-coupling reaction needs no introduction. Again, we heard lots about that yesterday. But I guess the speciation questions are pretty significant, and it's something that we and many others, Mimi being one of them, have cared deeply about over the years. And I guess where we're at the moment is that we know that soluble palladium species, so you might consider a simple palladium complex, that can find a friend to aggregate to form small clusters and nanoparticles, which grow to much more bigger particles, which ultimately precipitate out as inactive palladium black. The critical thing to say is that these aggregated species can play a role in the catalysis, not only in acting as a reservoir of palladium, but they can also act as catalysts in their own right. And of course, the shape and the size of these particles can influence their activity. More recently, we've been working with palladium clusters. So these are sort of well-defined palladium clusters, so triangular palladium clusters and linear ones. And these have been very interesting for us because they offer us an opportunity to study a smaller aggregated species and hopefully get some interesting catalysis results from that. But what we know from these linear clusters, and this is recent work that we found, is that if you take a mononuclear pre-catalyst like this one, that will find a way to get to these linear clusters where the triphenylphosphine is not just coordinated through phosphorus, it's coordinated through an arene. And of course, in these cyclic clusters here that I depict, I hide away the Y group here can be PPH2. And of course, that derives from triphenylphosphine. So some really important details here, just sort of connecting these clusters through to particles. But moreover, a more subtle point is that triphenylphosphine needs to be considered in different ways in terms of its coordination mode, but also the fact it can get converted to other things. And so diphenylphosphido being the obvious one. So it's gone from neutral to an anionic ligand in that situation. So what we know is the aggregated species are competent for catalysis, and we also know that speciation alters reaction outcomes. That's why I think we need to take it seriously. And I think simple models for palladium 0L complexes are really important, and there's loads of important work been done there. But I think this speciation issue, even for simple ligands like triphenylphosphine, really should make people a little bit cautious about how we interpret some of the results that we get from reaction outcomes, but moreover how we might model things in the future. So that's just to make I guess a point there about speciation. In terms of reaction outcomes, this is just to give you an illustration of why speciation is important. This is 2,4-dibromopyridine. You can get two products if you do a Suzuki coupling under these conditions here. Arylation at C2 is usually preferred. Many reports of that. The non-conventional product is the arylation at the C4 position, and you can get a little bit of bisarylation here. But what we know about speciation is if you get into a mononuclear palladium complex scenario, is arylation will take place at C2 here. If you get into a scenario where you've got a small cluster or nanoparticles, you'll get the C4 arylation product. So the speciation determines the site selectivity in that type of cross-coupling. So if you really need highlighting how important these things are, I think that's a really nice illustration of changing reaction outcome as a function of speciation. Okay, so again, sorry for the complex slide. I will make my slides available at the end of the conference. So you can have a proper look at these things, but it really gives you an idea of how we're using high-throughput experimentation, data analysis, and deeper learning. So this would be using the flow setup that Richard Bourne and Charlotte Willens have developed at Leeds. So having some sort of catalysis flow reactor system. Anna talked a little bit about this type of system yesterday, but here we've got an electrochemical reactor, so allows us to sort of generate catalysts on demand using Charlotte's approach. And hopefully you can have this full feedback control self-optimizing type system using that type of setup, and that's something we're looking forward to working with Charlotte and Richard on going forwards. You can of course think about screening in batch, and that's mostly what I'll talk about today, using a Chemspeed system, which I'll get to in a moment. You can look at reaction outcomes, offline, inline, or a variety of different techniques there. In terms of the reaction outcomes, we like others, and as we heard yesterday, we're using various ways to illustrate our data, whether that's through reaction networks, heat maps, or principal component analysis. We're sort of getting our trends from all of the different data sets using these approaches. And of course, we're still using the traditional techniques, so kinetic analysis and modeling and so on, to really understand mechanism in a useful way. And hopefully you can tie these things together and get a much bigger picture developing. So there's some knowledge here that I'll throw in. I'm not going to go through them all. Again, lots of these things were mentioned yesterday, but we're particularly interested in catalyst activation, deactivation, and side products as well, what they may tell us about reaction chemistries. These are the sort of processes we're targeting, so classic cross-couplings, CH functionalization, but going forwards, moving into organic catalysis and electrosynthesis as well. What I wanted just to flick through first is just analysis of some open data that's in the literature. So this is work, most of my work in automation is in collaboration with a mathematician, Julie Wilson, here in York. She has really has got me to understand some of the way that we can illustrate data, but she's an expert in chemoinformatics and has done lots of things with proteomics. So in good hands there, really, in understanding data analysis tools. So I'll just show you this paper by Neil Sack, Paul Richardson from Pfizer. They were looking at Suzuki couplings and high throughput experimentation using these nanoscale flow systems. So this is where you can screen literally thousands of reactions in a 24-hour period, and you can vary various things like your substrates and your different functional groups here, different ligands, different bases and solvents and so on. And they get lots and lots of reaction outcomes here. This is just product yield. So looking at this Suzuki product yield. And this is just a heat map. So the red is illustrating where there's high yields, and the blues where there's low yields. There was not really much data analysis in this paper. It was really about the technique and how you can get lots of data out. But they did, in their supplementary, make available all of the reaction outcomes with an Excel spreadsheet. And I got in touch with Neil and just asked whether they had any extra details on the side products that might be formed in this reaction. And they actually did. They had some information on some protoduborrelation side products. So we were able to get an enhanced form of this data set just by chatting with Neil, and he sent that to us. And so I guess we wanted to drill down a little bit deeper. So this is just this chloroquinoline here with this boronic acid. This is the cross-coupled product you've already seen, but this would be the protoduborrelation side product. These are common side products. Guy Lloyd-Jones has done so much work on this, understanding rates of protoduborrelation. So please read his papers if you want to know more about that. But it really is important, if we want to understand reactions in greater depth, that we map out these side product profiles. So you can do that with principal component analysis. And again, we heard about principal component analysis being a useful way to analyze large multidimensional data sets. So we can reduce that data down into the dimensionality of that using this type of approach. But without going into all of that detail, just to say that you can see here with principal component 1 along the x-axis here, and principal component 2 in the y-axis. So maximum variance in principal component 1 between starter material and product. So starter material data mostly with starter materials on this side, mostly with product on this side. But there we can see that the data points with lots of protoduborrelation is on this side. So this is actually a very useful scatter plot for just illustrating the importance of protoduborrelation from that SAC data. And I think it gives us much more insight. Now, again, we could spend hours and hours going through all of these different different data points and understanding what they tell us. But the important thing to say is that under a variety of different conditions, we see protoduborrelation, and it's something that we've been keen to drill down further. I'm just plotting this against the Tolman cone angle, by the way. Again, we heard Tobias talk about this yesterday, so hopefully I don't need to give more details there, but just to show you that does influence the amount of protoduborrelation. Triphenylphosphine, I always like to highlight triphenylphosphine because it's that ligand that is often, people will go to more complicated ligands for cross-couplings, but actually in this case it sort of sits between starter material and product, even for a chloroarene. So this is about 63% yielding reaction for triphenylphosphine. So just highlight that really. And the other thing to say is that we can look at this just for a different reaction here. This is where we've got the bromide. This is where we've done the umpalung. So the bronic acids become the bromide, and then that chloride's become the bronic acid. So the same product, we've got a different protoduborrelation product, and you can plot this as a function of solvent and different ligands here, just looking at the directionality here. So protoduborrelation in this side, product on this side, and then starter material down here. And so what you can see is there's a distribution, and you can see a lot of spread for different solvents here. Again, I don't wish to go into the details here. It's just to show you the value in the data that you get. The red dots are actually of reactions that we've conducted using batch screening in York. So this is all done with that nanoscale flow. You can see it's all kind of skewing towards this protoduborrelation side product. We don't see that actually with the reactions that we screen with different catalyst systems, including Palladium clusters. So Palladium cluster, you can see, is a very active catalyst for this type of reaction, but it gives you an indication that, you know, when you're screening in batch, you might get a slightly different outcome to what you get when you're running these reactions under high pressure. Okay, so the sort of, I guess, the next sort of 5-10 minutes or so, I just wanted to talk a little bit more detail about how we've been using that principal component analysis for probably one of the more complicated reactions that you could look at. Again, it's in collaboration with Julie, and I was just hoping that we could use high throughput reaction screening in a better way to understand these complex reaction chemistries. This is a perplexing reaction, actually. It's one that's been known for a while. It's been published by several groups. So it's where you take these brominated benzoamide type starter materials. You take two of those together and you form a phenanthridinone product. Now I've colored these so you can see where everything's come from. So two of these molecules come together to put these two arenes together, and then one of the amide remains to form this cyclic phenanthridinone cyclic system. You can form it under different reaction conditions. It is a peculiar reaction, and if you don't put the two in front of that, people will often look at this and say, what's happened there? But as long as you know there's two equivalents that come together to form that, then that's the important detail. But a variety of different ligands, different reaction conditions, very limited mechanistic detail on that. Now, the mechanisms that are published, without going into the details, involve classic steps, so oxidative addition reactions. In most of the mechanisms proposed, they go via Palladium-4 intermediates, and eventually you eliminate this phenanthridinone product. You see side products as well. Some of those have been isolated, some not. But the problem with these mechanisms is oftentimes the ligand's not shown as being part of the intermediate. And for a Palladium-4 intermediate like this, it's not clear to me how the ligand would be involved, Palladium-4. So there's real questions over the mechanisms here. So we've done some control experiments just to show how this all works. So you really do need two equivalents of that starter material to get the phenanthridinone product. You can deuterate the phenyl ring and show how this all maps together, and you can even put a substituent on the ring system here just to show the connectivity and how that all works out. We know that we've done some kinetic analysis on this reaction, so if you do a preheat of the pre-catalyst palladium acetate and DPPE, you can avoid you can avoid having a significant induction period in that system. But having a cold system isn't that detrimental. The overall conversion is affected, so the overall kinetics are affected, but it's just to say that you do see a difference, and that's just, I highlight that just because I think that can be important for screening studies. So with that, what we know, and this is where our high throughput experiments come in, we know that all sorts of things can happen with this molecule: CH activations, carbon halide activations, CC activations, CN activations, and so on. So all sorts of products can form, and there's 17 here that we've characterized in this type of chemistry. So a lot more than what's been reported, including unconfirmed species. This is all, these have all been independently characterized, I should say, except for the unknown species. And we also see other things by GCMS. So these are other species that just one needs to be aware of in the chemistry. So very complex chemistry. How we're going to screen the reactions? Well, here we utilize a Chemspeed system. So as Rebecca talked about yesterday, it's a similar system. So again, I won't go through all of this because we had a nice introduction to how this system is used. Some lovely papers by Melody Christiansen and Jason Hine. that show how the Chemspeed can be used, but also Verinda has had a very nice paper just come out on sequential syntheses, so sort of multi-step reactions in one automated flow process, which I think is fascinating. So here we can look to change variables and screen reactions in a kind of high throughput way. So some of the issues I wanted to make you aware of with the Chemspeed system, some of this will probably be very obvious, particularly if you had a water DCM mixture. But when you're mixing solvents for this sort of system, you have to be kind of aware that, so I'm going to have to come off the, so you have to be aware that we're using orbital shakers for these reactions. So you can see this is just how these swirl. This is at 300 revolutions per minute, and then of course if we speed that up, you can see that still the mixing isn't great, and then again you can go to 500 revolutions per minute, and you can still see there are dead spots within this particular vial. So it's just to be aware that the systems we're using have got orbital shakers, and the mixing for biphasic systems can be sometimes problematic. We also, there is an importance to do technical replicates. It seems obvious with high throughput screening you'd want to do that, but sometimes when we're screening multiple reactions on a plate, you might not see any sort of positional variability at all. This is the case in an amination reaction that we've looked at in the past, but in the case of another reaction, this is a Suzuki coupling with an elimination to give an alkyne, we have seen some positional variability, and that's come down to air effects in that chemistry. I'm not going to go through that, but I'll be happy to answer questions on those air effects in terms of the actual the Chemspeed system, if anyone wants to know more there. The workflow, we have one of these, and I mean, most people are using these, I think, to illustrate how the automation's working now. So I won't go through all of the details. That it's there. I'm happy to talk about it. But the important thing to know is that we're screening solvents with temperatures. We have various time points, and in a particular system, we might be looking at, you know, sort of 400 or 500 reaction data points for this type of chemistry. We analyze the data. Well, we're analyzing the reactions by LCMS, and that gets exported into some software called Progenisis. And that allows us to look at all of the peak intensities, both from a UV perspective, but also from an ion count perspective as well. We can get the data out from that reaction. So this is changing those solvents, it's changing the temperatures, looking at the different times, and get a feel for how things are responding by principal component analysis. Now, this is very complicated for all of those different products, and I do apologize. That's how it looks for this data. The important thing to say is that the major product, which is this one here, the phenanthridinone, is down in this direction here. The side product, the major side product, this one here, appears sort of in this sort of zone here, but all of the other things factor into this. So this is where we're looking at reaction times and different solvents. Here we've got temperatures and different solvents as well. So you get a feel for how the reactions are responding to temperature and solvent, as well as the reaction times. And these, you can almost think of these as sort of like kinetic profiles, because we go from the small dot to the bigger dots from 1 to 8 hours. So there's almost like a pseudo temporal profile of the reaction progress. So we get quite useful information from that. This is where we've just omitted. So here we've got some outliers, and we've omitted 13 outliers really to sort of tease out a little bit more detail. So you can get some trends from this, but you can see it's incredibly complicated, and working out how and what correlates is very, very difficult. So what we've done is use heat map correlations, and so this is actually probably the most useful tool we've got at the moment for these complex reaction networks. So this is where we can show correlations between products that are forming under the reaction conditions, and that's as a function of those solvents, the reaction times and temperatures. We can also put in our technical replicates into all of that as well, but we can start to see that things start to hook together. So certain products seem to be associated with each other, as I'm highlighting here. So that's the major product here. This is a post-functionalization product. We also see an oxidative cyclic product that seems to result from 2A here. And we also see associated with that with a dehalogenated starting material as well. So there's some really nice correlations that start to give us information about how things might be connected. And so from a mechanistic perspective, we can, of course, come up with mechanistic proposals. I should add as well that what we do know from independent mechanistic work is what type of catalyst species that we're generating. So we know we're starting off from a palladium 0 DPPE complex, as we can characterize these species and the reduction process for that. We can also characterize the oxidative addition product and also this intermediate that's downstream as well. So we've got complementary information here about the species that are present in the reaction mixture as well that will lead on to these products. The important thing to say is that when this compound is liberated from the palladium catalyst, it doesn't go back in to form this product, even though it looks like it might be able to decarbonylate and do so. It doesn't do that. So that has to stay at the catalyst down in this region down here. And so those correlations I showed you from the heat map hierarchical clustering, we can start to see that, you know, one product associated with another. So this oxidative cyclic product here is associated with the debromination or proto-debromination of the starting material to give you this. This balances the redox process for the chemistry. Again, without going into the detail, just to say that that works out really nicely. So we've not got a detailed map of that reaction. We just know that the two are coupled, and we can come up with a more sensible proposal based on that observation. The other correlation is this post-functionalisation of 2A, the major product. So we know that if that major product comes back in, it will react with the oxidative addition product. It can go through this sort of intermediate. I apologise for putting steps here. As a mechanistic chemist, I struggle with this, but it really, we don't know what's going on fully. But what we do know is that we form a product that looks like this. So we've got this post-functionalisation product. And the correlations from the high throughput screening show that they're connected. And then lastly, we have a correlation with 3 different types of products. So 5A is this product here, and 13A is this product here. So this is where we've got this intermediate that you've seen before, but we've got a hydrolysis of that amide to the acid. We detect that. We also see aniline, and we can detect that and quantify it. So those 2 things connect. As does this product here. So again, it allows us to come up with some sort of sensible hypothesis for the mechanism as well. So competing catalytic cycles and correlations that are revealed through the high throughput experimental screening, which I think is fantastic. So it's been a whistle tour. Sorry, I've been very, very quick, but hopefully what you've been able to see is that we're able to use high throughput experimentation and data analysis and how that complements the mechanistic work as well. We've got a really difficult chemistry that we're looking at here. The principal component analysis is useful in revealing trends in the reaction data, but it's not the be-all and end-all for this type of approach. I would say that the big thing from me today, if you can take anything from this talk, is to say that heat map and hierarchical clustering is just really useful for correlating lots of side products that are formed in your reaction chemistries. And I'd just make the point that mapping out, you know, the majority of your reaction products will really aid reaction understanding and the interplay of these competing pathways. And of course, hopefully you would see that potentially opens doors to serendipitous discoveries, as well as we were kind of talking about yesterday in the discussions as well. I've tried to name people, acknowledge people in the slides, so hopefully I've done that. I'll just finish with some photographs and thank you for your attention.
Thank you very much, Ian. It actually stops the time, which is really good. So I remind the audience again, the chat function is open. I don't see any questions there, which is good, because then that allows me to ask all my questions. So I hope you don't mind, Ian. So the batch versus flow is very interesting when you run the batch reaction versus nil-sex. So one obvious thing I can think of is, of course, in their reaction, it's only 1 minute. So your reaction mixture is exposed to a very high temperature very quickly. I assume your batch is done by warming it up. So how much of that do you think is a temperature effect? And if at a different temperature, maybe less protoduborrelation?
Yeah, I think, we certainly don't have that. We have a lag period for sure. And we're looking at a couple of hours as well in the batch system. I guess in some ways, I've been thinking a lot about this. In some ways, that you know, they really aren't comparable. I guess the worry is it's when you're trying to use the data. So I guess, you know, under those conditions that you are likely to get more protoduborrelation, and that's what I take from that data really, and perhaps highlights where there are sensitivities. But we're just finding that whenever we screen that reaction in batch, we don't see such significant protoduborrelation, which is probably a good thing, because when you scale up, of course, you don't want that as a side reaction. So I think, you know, there's pros. I mean, of course, with the nanoscale flow screening, they can screen 5,000 reactions in 24 hours. In batch, we'd be lucky if we've got, say, 160 or so in 24 hours. So it's kind of that they get the acceleration in that nanoscale flow screening process that we don't. They did actually do some batch screening in their paper, but they did it for their really high yielding results. So they showed it scaled really nicely actually in batch. But I would have thought that the more interesting ones, certainly from a mechanistic perspective at least, and I'm sure that wasn't a driver for them, it would just be to look at the ones that were lower yielding. So that triphenylphosphine result that I've highlighted, I actually think that's the one to go after, but it's because I'm obsessed with triphenylphosphine, I want to hunt that one down, because I think it's one of those ligands that people just think, well, it's the one I learned in undergrad, but I can use a fancier ligand now. I don't need to use triphenylphosphine, but oftentimes it can be the one that's quite, obviously it's cheap. So, you know, if you can get a synthesis to work with that, then great.
Okay, so I can see Will now have a question in the chat box. So this is about the model, actually, your clustering, sorry. So the question is, how does hierarchical clustering compare to other clustering methods? For example, k-means clustering when applied to your data.
Yeah, we've not done that. We've not done that analysis, and that's something that we would need to do. So I can't really answer that question fully.
Because following up on that, I also noticed that you clustered them separately, right? The couple product as one, and for example, the deboronation product as another one. But if you see them as competitive things, what happens if you express it as a ratio of your product versus would you actually get a different picture? Because then you have the kind of, effectively, if you see them as competitive processes, right? Maybe the difference between your activation energy, maybe that reveal a different kind of landscape. I don't know. Did you try to do that?
No, we haven't, but it's a great idea. Thank you. But yes, no, we'll look into that. So 2 suggestions that we can look a little bit closer at there. But it's interesting to sort of think about that, whether we can actually tease a little bit more info about how important these different catalytic competing cycles are. What's the dominate? You know, you sort of think about primary cycle, secondary, tertiary, and so on. If we could put some sort of weighting on that, that'd be great, wouldn't it?
I mean, that's assuming that it's the same catalyst, of course, because you talk about speciation. So I guess you didn't. I mean, I guess you didn't go into it in much detail, but it's also possible that different palladium catalysts give rise to all these mixtures that you see in the end as well. So
I'd love to be able to show you more data with different ligands, and you know, that's something that we'd like to do in the future as well. It's funny, isn't it? You see all these publications where they do all of these different changes. I mean, ligands are probably the obvious one, as we saw yesterday from Tobias's talk. With this being such complex chemistry, we've had to kind of focus in on characterizing all of those different side products rather than just focusing on the major product. So we've kind of, if I can make an excuse, been distracted by the complexity of the system because of all the different side products. And actually, what would be really interesting to drill down into is, you know, if we change that ligand, what happens? And of course, we know from the literature that the ligand does have a profound effect. And so there's a lot more for us to do on this. One of the questions, and we've had our initial reviewers' comments back for our paper on this. You know, one of the questions has been, well, is this really a novel enough reaction to be looking at? And because it's already known, and that is
that old chestnut. Yeah, sure.
And it is a real problem. You know, of course, it's okay to have lots of high throughput Suzuki stuff, which is a well-known reaction, but of course we need to know so much more about Suzuki couplings. I think what I was trying to do with this chemistry is, I mean, it's just an exemplar piece of chemistry that's got loads of side products. And I think if you kind of take a step back and think about, well, if I've got I don't know, a pharmaceutical active ingredient of some type, then you know, I'd like to kind of know about my sensitivities to the reaction and what side products can form, because you can imagine this being quite a detailed, you know, this could be used in various different ways, this approach to sort of really understanding reaction chemistries and sensitivities, and informing, you know, what might form as a trace product in a reaction and feed downstream. You know, you think about all of those things with nitrosamines, which are now in a lot of people are talking about those things. And so mapping out all of these side products, I think there's great value in it. And I think that's what I was trying to put the weight of the novelty, was to say, well, no one's really looking at these complex reaction networks and all of the different side products from that perspective. So I guess the chemistry was a means, you know, it could have been anything really. It would have been lovely if it had been novel chemistry, but the reality is we've identified what is probably one of the more complex palladium catalyzed reactions that you'll ever see.
Yep. Okay, so there's 2 more technical questions, so I'll leave the rest of the time to to these questions. Yeah. So the first one is from Natalie. Natalie, do you want me to read it out or?
Mind, I can just ask it. So Ian, you talked about these technical replicates, and as a data person, I was wondering whether, rather than detecting it after the event, you've looked at ways of actually detecting it whilst the reactions are still going on, and potentially folding that into some form of meta tagging of the data. And I guess I was sort of thinking about what Marguerite is doing with color and detection there.
Yeah, I mean, when we sat, I mean, the first thing to say is, I hope I've got the right end of the stick here, Natalie. You know, the reactions are effectively quenched when we sample. So
okay,
the sample we take at that time point is reflective of that time point. I can talk to you at length about reactions that do continue in HPLC and GC vials. I've seen it so many times.
But you're not sampling time series normally. You just do an endpoint sample and then analyze the mixture.
Well, if I just go back, sorry, I really rushed over this data. So here we are looking at sample points at 1, 2, 4, and 8 hours in this PCA plot. So I was kind of trying to draw attention to this. So just on the directionality, we've got major product 2A, this phenanthridinone, down in this area. Start material 1A is on this side. So you can imagine what we're seeing here is effectively more product after 8 hours than you do after 1 hour. I mean, that's sensible, right? And you see that in these different solvents. So this is dibutyl, N-dibutyl ether. This is toluene here in dark blue. You can see the solvents where the reaction works really, really well, where you've got predominant product as well. So in a sense, you have a temporal profile for reaction progression there. But of course, you've got all of these things feeding in, and it doesn't give you rate information for, you know, each one of these species. It's just a kind of a, could you call it semi-quantitative temporal profile? I don't know, but if you're basing consumption of 1A, it's probably okay.
So what I was kind of thinking about was that you could have metadata on top of that saying, okay, here there is a problem with solubility, or something has become biphasic. At that moment in time in that vial, there's a color change, and actually start tying that sort of information into your analysis as well.
That sounds perfect. Yeah, I mean, one of the obvious ones is you form palladium black. I mean, you know, and historically people used to see palladium black dumping out of a reaction as meaning the reaction had completed, and if it dumps out in the first few minutes, your reaction has failed, something's gone wrong, you know. But actually, I mean, Mark Reed at Strathclyde has done a little bit of this, hasn't he, on the
yes.
colour changes. Yeah. And yeah, when does the reaction go black is quite a useful one, because that tells you when that palladium's precipitated. With these reactions, at the end of the reactions, they are black. I'm not going to hide that away from you at all. So that sort of, I guess those color changes would be useful for us as well. So in situ, we'd love to have in situ and more in situ information as well on these.
Yep.
I guess these questions, though, I guess I'd be wanting to use those those approaches on a simpler system. I think this is a, you know, as a reaction system, it's probably the most complicated one that we could ever look at.
Oh yeah, it's a mad one to prototype, but at the same time, if you come at it from the general direction of data collection, what you actually want is to create this really rich data environment. So you've got it, and then when you find variability in your product distribution and many other things, you can go back, relate it to when you took the different time points, when you quenched the reaction, and say, okay, what actually else is happening? Is there, you know, is there a color change? Is there evidence of a change in viscosity? Would there be a massive change in temperature? All those sorts of things, and actually start to tie it together. I know that's incredibly hard, by the way.
Sorry. I hate to interrupt, but
no, that's fine.
I've been told that we had to move on. I can see that's already simulated quite a lot of discussion already. Actually, there is a question also from Abraham about processing of data. But I'll ask Abraham and everybody else to hold on, because I suspect our next speaker might actually address that question. So a virtual round of applause again to Ian for